Hey everyone, welcome to Introductory Physics, and this could possibly be your very first course in physics, which is really exciting, and we are here to help with a series of videos that pretty closely follow Young and Friedman's University Physics textbook, which is a very standard, great introductory physics text. Alright, let's jump right into it. So, when it comes to the nature of physics, people tend to argue whether theory or experiment comes first. But I, for one, think that that's sort of a chicken or the egg type of problem, because the truth is, experiments allow us to see patterns and formulate new theories, but theories inspire new experiments so that we can begin to test if the theories are right or wrong. And that will ultimately take us all the way back to the very first time someone ever formulated a theory or performed an experiment, and that begins to go into the world of history of science. And in introductory physics, we don't concern ourselves that much with history of science. But speaking of history of science, I want to very quickly take the example of Isaac Newton. You have probably heard of him. Legend has it that an apple fell on his head and he came up with the law of gravity. But in actuality, we don't know if this is true, and his intellectual efforts and experiments were far more complicated than just observing an apple fall. Now, it turns out that Newton's law of gravity, which we will talk about extensively in later videos, didn't seem to work in environments where the gravity is extremely strong. Albert Einstein was the one who came along and proposed a new theory of gravity, that is general relativity. But I want to emphasize that this does not mean that Newton was wrong. It just means that Newton's law of gravity has a certain range of validity, and it just so happens that the force of gravity near, say, a black hole is not in that range. The nature of physics is, and has always been, to come up with models, which are simplified versions of actual physical phenomena that occurs in the real world, but that sort of capture the major behaviors of the system in hand. All Newton did was come up with a model to begin to describe the forces of gravity we see around us, but just because Einstein came up with a better model doesn't make Newton's model wrong. In fact, Newton's model is so good that we still use his laws of gravity and laws of motion in physics when the effects of relativity are small. Alright, now back to our study of physics. One model that we use often is to assume that an object is a particle. And what we mean by that is, for instance, if we wanted to study the motion of a ball under the force of gravity, we want to first be able to study gravity on its own without considering complicated things like air resistance or the spin of the ball. So, we assume that the ball is a particle, just a point with a certain mass attached to it. Since it's just a point, there's no air resistance and there's no spin. Of course, this model is not entirely accurate, but it is enough to begin to capture the essential pieces of the motion of objects under gravity. Okay, so in this video, we talked about theory versus experiment in physics. We talked about models and range of validity. And we talked about a specific model, the particle model, that we often use in physics. And that's about it. So we will see you next time when we will start to talk about physical units.